Okay. Any questions about yesterday? Reading for today? That's a no. I mean, some type of answer would be really helpful. Well, the theme for today is going to be amines, and then starting into carboxylic acids, because we didn't do any amines yesterday, but that's okay. One thing I want to go back to. So yesterday we sort of finished up the idea of ketones and aldehydes with our protecting groups, and using the cyclic ketals and acetals as protecting groups. Back in the alcohol section, there was also protecting alcohols, and I didn't go through that in class, but now would probably be a time to talk about, just to kind of review that. So yesterday, if you don't remember, and if you don't, it's only yesterday, what we said was that if we have multiple functional groups in the molecule, let's say for instance, I had like a double bond and the carbonyl, and I wanted to protect the carbonyl and do something with the double bond. The way we would protect it would be to basically then take our ethylene glycol and H plus and protect the carbonyl as the cyclic acetal, or in this case the cyclic ketal, and then that would let me do something with the H plus, or would let me do something with the alkene. And this cyclic acetal is going to be stable to all reagents but acid and water. So I can do anything I want to that double bond except use acid and water. And I could use acid and water, but then it's going to take the acid or the ketal all the way back down to the ketone. So I could do any reactions except H plus and H2O, because H plus and H2O are going to drive the equilibrium back to the ketone. So that's the way we were protecting ketones and aldehydes from reacting if I wanted to do something else to the molecule. The method that was talked about in the alcohol section was a way to protect the alcohols from their reaction. So, for instance, if I have an alcohol, and let me just make something up here. Let's say I had this molecule and I wanted to make some polyalcohol where I wanted to convert that double bond. I wanted to add 2 more OHs to where the double bond is to make some trialcohol. And I want to start from this molecule. First of all, what reagent would I use to convert the double bond to the diol? So how do I add 2 OHs cis to a double bond. I can wait you out. It's tough, but I can do it. BH3 and H2O2 will add one OH and the H anti-Markovnikov cis. I want to add two. I want to do what's called Sis Hydroxylation. So I could use OSO4 with H2O2. That's one set of reagents. There might be another set in your notes there as well. KMNO4 and base. So either one of those reagents will add two OHs cis across the double bond. What's my issue here? If I wanted to use potassium permanganate, is that going to react with this? Is that going to react with that OH? And what's it going to do to it? I don't know what that means. Put in some language that I can understand. Like the potassium, like the KMNO4 will oxidize the alcohol to a ketone. So the KMNO4 or even the osmium tetroxide, and it's not so much the osmium tetroxide as it would be the H2O2, is going to oxidize that secondary alcohol to a ketone. So if I tried to use these reagents, I'm going to end up with the ketone. Yes, I will end up with the two OHs here, but I'll end up with a ketone here that I didn't want. I didn't want to oxidize that original OH. So one of the ways we can protect an OH group is, we could convert it to an ester. And sometimes people will do that. But in the book, they talked about using what's called a silyl reagent. So one of the ways to protect alcohols from further reaction is to protect them as a silyl ether. So what does that mean? That means that if I take my OH group here and I react it with a silicon, usually a silicon with three methyls, although you can have various arrangements of alkyl groups, but we have a silicon attached to a chlorine. And what's that going to do? Well, what happened when the sulfur was attached to a chlorine? I'm going to basically lose HCl in this process, and I'm going to go ahead and add what's called a trimethylsilyl group to the alcohol and make a silyl ether. That silyl ether is stable, and so that O group will not react. It's going to be protected. So this would be a way to protect an OH group. So back in that chapter, they talked about, okay, we can make a silyl ether. So then I could take the double bond and I could do whatever I wanted to it.
Where is that extra bond right there?
Wasn't it in the original molecule? No, it wasn't. I thought it was in the original molecule. If you're going to protect, you got to deprotect. So how are we going to deprotect? One of the strongest bonds that you can form is a silicon-fluorine bond. So what we would do is we would either add sodium fluoride or potassium fluoride or even cesium fluoride to this, and what will happen is that the silicon-fluorine bond will form, and that will release the oxygen back to an OH group. So you can put a silicon group on an alcohol or on an oxygen, and then using fluoride you can remove it because that bond is really, really strong. So this was a way to protect the silyl ether, or protect an alcohol using a silyl ether. And it's sort of analogous to what we did yesterday with the protecting of ketones and aldehydes. And like I said yesterday, in terms of looking at like sugar chemistry, a lot of syntheses, a lot of when you're taking A to whatever molecule you want, you know, whether it's not normally A to C or A to D, it's more like A to M, or even through the alphabet. When you do that many reactions, you do have to protect groups as you're reacting other ones, and then deprotect, and then protect those other groups. So it's a constant protection, deprotection kind of a scheme that you have to use. And so these are just two examples of how you can do that. So this one I didn't talk about back when we talked about alcohols, but it's relevant. Okay. So the protection deprotection was the sort of the end of the ketones aldehydes chapter, and we'll come back to that here in the amines today as well, because there are ways to make amines starting with aldehydes and ketones. So does this make sense? So this wasn't on the alcohols exam, but it could be on next Monday's exam. So this is how we protect. This is how we protect an alcohol. Okay. All right. Now, amines. So amines, the amines we have to define the types of amines that we can have. So we can have 4 types of amines. Depending on what's attached to the nitrogen. So you can have 0, 1, 2, or 3 alkyl groups attached to the nitrogen. We designate these by saying, okay, given the number of alkyl groups that are on the nitrogen, it's either primary, secondary, or tertiary. So an NH2 is going to be a primary amine, an NH is going to be secondary, 3 alkyl groups is tertiary, and no alkyl groups is simply ammonia. And ammonia is useful, but it's not technically an amine. The amine has to have an alkyl group on it. So as we're looking through these amines, it would be helpful to have a way to synthesize each one it would be helpful to talk about basicity of amines. It would be best to talk about nucleophilicity of amines, and then how we can make the different amines and how we can react to different amines. So that's kind of what we have to talk about. So first is basicity. So amines are basic. You know, when you put an amine into water, that you get an equilibrium between the ammonium and hydroxide. So this is a Kb equilibrium, not a Ka, not because amines are not acidic, they're basic. Put them in water, they take a proton away from water, they don't give up one. Now you might say, but we've used NH2 minus, so that must mean we took an ammonia and deprotonated it. Yes. And that was using the strongest base on the periodic table to the left of nitrogen, which is carbon. So if we want to make an N minus, we need to use a C minus to make that. But we'll come back to that. So this is the Kb equilibrium. And so remember that minus the log of Kb is called the pKb. Minus the log of anything in chemistry gets a little p in front of it. So sometimes you'll see these molecules listed as having their pKb's. What's a stronger base? Something with a low pKb or something with a high pKb? So let me give you the list. Here's ammonia. Here's a primary amine. Here's a secondary amine. And here's a tertiary amine. And here's their pK. This is the listing of their pKb's. So ammonia is 4.7, 3.4, 3.3, and 4.3. Okay, and for some reason the book doesn't like to do this. They like to show pKa's, and that just confuses me. So I want to, if I'm measuring basicity, I want the pKb. I don't want the pKa. There's too many inverse relationships in chemistry as it stands, so I want to deal with a direct one. But if I asked you, okay, which one of these is the strongest base? NH3 or right? If this is our multiple choice strategy, right? If I said which one is the strongest base, you would have it narrowed down to 2, knowing nothing. Right? So then the question is, well, which is it? So the way I remember pKb's is pKb, pKa is like pH. If I said I have a solution of pH of 4 and pH of 10, which one is more acidic? You would say the solution is pH of 4. So the lower the number, the stronger the acid, right? So the lower the number here, the stronger the base. The P scale works exactly the same. So which one of these is the strongest base? R2NH is the strongest base. Why? Because it has the lowest pKb number. Okay, so pKb works exactly like pH. Lower the number, stronger the base. course, I guess now we are obligated to talk about why. Why are these, first of all, why are all of the amines with an R group on them more basic than ammonia? And why doesn't it go primary, secondary, tertiary, or tertiary, secondary, primary? Why is the secondary the most basic of all? Okay. So, we can do that by going back to basics. What? What? True. There wasn't any when I didn't figure out the joke immediately. How about we go back to fundamentals? Here's our equilibrium that we're looking at, right? We're taking a B for base, reacting it with water in an equilibrium that forms a BH plus and an OH minus. How do I make a stronger base? Shift the equilibrium to the right. So I want to shift the equilibrium to the right. Give me some strategies that I can use to do that. Again, going back to the fundamentals. We always start with Le Chatelier, and Le Chatelier just doesn't work in this case. All right, related to resonance structures, when we've used resonance structures in the past, how has that made a stronger acid? Because there we were looking at another equilibrium, right? I usually don't write the water, but I will this time, and a plus. How did resonance structures play into making HA a stronger acid? It was usually this that had all the resonance structures, right? And so what did the resonance structures do to A minus? Made it more stable, and making the conjugate base in this case more stable did what to the equilibrium? It pushed it to the right. So let's use that fundamental on bases. What should I do to make a stronger base? Make what more stable? Your choices are B or BH plus. Make the BH plus more stable, because then the equilibrium will shift to the right. Okay? How do you make BH plus more stable? Add an alkyl group to it. So now let's go to nitrogen. Now let's not deal in sort of generalities. Let's go right to the amines. So if I have an NH, if I have this, how does adding an alkyl group to the nitrogen make it more stable? To the N plus, how does it make the N plus more stable? I have hydrogens on the carbon. How does it do that? You're getting there. What do I need to do? What's the alkyl group going to do to make this more stable? By equalizing the charges, what do you mean? No. That would be resonance. That can't happen with this carbon. How about the carbon-hydrogen bond? It's relatively nonpolar, covalent, but what do we do? What have we done with carbocations, with radicals, with double bonds, with triple bonds. In all those cases, the more alkyl group, the more stable. Why? Carbon, hydrogen, who's delta plus, who's delta minus? Hydrogen's delta plus and carbon's... Come on, if that's right, it's got to be delta minus, right? Okay, so the carbon's delta minus. What can that carbon with the delta minus charge do now? Is it going to hoard a negative charge? It's going to push some of that electron density towards the nitrogen. What's that going to do? Make the nitrogen less positive. So in a way, kind of equalizing the charges. But it'll never completely equalize it. So how many times have we invoked this summer? Well, I think I said it 4 times. More alkyl groups on a carbocation, more stable the carbocation. More alkyl groups on a radical, more stable the radical. More alkyl groups on a double bond, more substituted, more stable. Triple bond, same thing. Carbonyl, right? Why is a ketone more stable than an aldehyde? 2 alkyl groups versus 1. What's the most unstable aldehyde? Formaldehyde with 2 H's because 0 carbons. So that's 6 times that we've used this principle. This is number 7. So if I want to stabilize a nitrogen plus, push electron density into it. There's a sentence in the book that says, if you want to make a nitrogen more basic, push electron density into it. That's the fundamental. If you want to make that nitrogen more basic, push electron density into it. Okay. So, question number 1, going back here to the ammonia versus the alkyl amines. Why are the alkyl amines more basic than ammonia? Because they have an alkyl group attached to them. What is that doing? That is stabilizing the conjugate acid, pushing the equilibrium to the right. So question number 1, why are alkyl nitrogens more basic than ammonia? Because alkyl groups stabilize N+. Well, we're not there yet. So that was just question number 1. Question number 2 and maybe 3 and 4 are going to be, now let's look at the intricacies of the alkyl groups. And why do they go secondary, primary, tertiary, and not like primary, secondary, tertiary, or even tertiary, secondary, and primary? Okay. Because if this was the case, if just adding an alkyl group to a nitrogen is going to make that nitrogen more basic, 3 alkyl groups should be better than 2, better than 1. And that numerically is not the case. So there must be something else that goes into this. So what is that? Amines, whenever we measure acidity or basicity, what solvent are we using? we're always using water. Now, not always in organic chemistry. There have acidity and basicity in organic chemistry is much more difficult a topic than it is in general chemistry. Because in general chemistry, we work in water. When we have organic molecules, the first thing they have to do is be able to be dissolved in water. And since most of them can't be, how do we measure acidity and basicity? And maybe we'll delve off into that, but it's not as simple as just water. So the solvent is water. How else could I stabilize BH+? Add an alkyl group, push electron density towards it. What else could I do to make BH+ more stable? So in other words, what's the other factor we have to take into account? We'll come back to that with aromatic rings. What was I just talking about? This might be the problem. What was the other topic I was just talking about before I asked this question? What question did I ask you? I'll ask it again. What's a solvent in this reaction? Water. Now, being a professional educator, organization is the key. Sometimes. If things are disorganized, people can't understand. They got to cut through the disorganization. So, everything I do has a reason behind it, most of the time. So why am I asking you what the solvent is? What do you think the other factor is that can go into stabilizing the BH+? What does it have to do with? Solubility or the solvent stabilizing the plus charge? Solvation. Oh, I'm having a sense of deja vu again, but probably from last class, from summer 1 or 2 or whatever it was. But we might as well review. Maybe it's all the tangents. The tangents all have a point. SN1 reactions, where I'm going to take my alkyl halide and I'm going to form my carbocation and my chloride. What kinds of solvents make SN1 reactions go faster? Protic. The protic solvents. So in other words, water and alcohol. Why? You only got 3 things here to solvate. So yes, it's going to solvate something better. By solvating and the chloride. So water and alcohol are going to solvate the carbocation and the chloride better. What's that going to do? In this case, it makes the reaction faster. Right? Your delta minus oxygen will solvate the carbocation, and your delta plus hydrogen will solvate the anion. Okay. So we've seen solvation cause this reaction to be faster because it's solvating the products. It's helping stabilize the products. So let's go back up here. What other factor goes into shifting this equilibrium? Will water solvate the BH plus better or worse as we go from primary to secondary to tertiary to ammonia? Okay. So if water will solvate the BH plus better, it'll push the equilibrium to the right. If water will not solvate BH plus as well, then what happens? The equilibrium doesn't get pushed as far to the right. So solvation is the other factor here, and that solvation may or may not be going in the same direction as an alkyl group. For instance, which one of these two is more water soluble? Or which one of these two will water solvate better? Primary or primary ammonium or tertiary ammonium? Why? Well, PKB is going to be a combination of both the solvation and the adding of the alkyl group. So forget about the PKB value. Just which one of these is going to be more soluble than the other. What happens when you put an alkyl group on a molecule? Does that increase water solubility or decrease water solubility? What did you say? Do you agree with them? Do we agree with them? Did more alkyl groups decrease the water solubility? Hydrocarbons are nonpolar. So the more alkyl groups or the longer the alkyl group chain, what happens to the water solubility? It decreases. So a tertiary ammonium, because it's got 3 alkyl groups, is going to be less, this is going to be less water soluble. Although this is, I'm going to put the solubility in quotes because it's an ammonium salt, it's ionic, so it's got to dissolve in water, but there's going to be less solvation. So it's really less water solvation around a tertiary versus a primary. Okay. So we have 2 factors that go into this basicity. Number 1 factor is, in theory, the more R groups, more electron donation, lower PKB, more stabilization of the N plus, the NH plus species. So in other words, the more alkyl groups, the stronger the base should be. That's factor number 1. Factor number 2, more R groups, less stabilization of NH plus by water. Are these two factors going in the same direction? No, they're going in opposite directions. And so this is why the pKb numbers did not go either smaller or larger from primary to tertiary. Okay? So these two are opposing each other. These two factors are opposing each other, and so in some cases one is going to be stronger than the other. And so this is why we get the values that we get. So if we go back and we look at the pKb numbers that I gave you that aren't in your book, I had to Google search those, which is really easy. Just Google search pKb of amines, and it'll give you a chart. If we look at these two factors, we can tell which one is more or is stronger for each of the 3 or 4 types of amines. So if I go back to the beginning here, why is ammonia the highest? No alkyl groups. So the alkyl group plays a significant role. But now looking at primary, to secondary to tertiary, why is the secondary the strongest base? Well, because there's a solubility issue here. There's a solubility issue between secondary and primary. And then there's a huge solubility issue here with the 3 alkyl groups. So actually, the solubility of the N plus species explains why tertiary is at 4.3. Because with 3 alkyl groups, stabilizing that plus charge is really bad. So it counteracts the 3 alkyl groups. Now you might say for these remaining 2, they're pretty similar. So where's the solubility issue here? Well, the solubility issue here is not necessarily from the 2 alkyl groups, because remember, when I added a second alkyl group, that should have made the secondary much more basic, right? So we have to look at it from, oh, the primary has somehow been elevated to be equal to the secondary. And so what elevated the primary? It's more solvated by water than the secondary. So that's what elevates the primary up to be nearly as strong as the secondary. So normally we'd expect the primary to be like, I don't know, it would probably be, we would expect the numbers to get lower as we go across for primary, secondary, and tertiary, and that's not what's happening. And that's because of the solubility. So primary and secondary are roughly the same. Secondary should be much stronger, but the solvation is elevating the primary up to where the secondary would be. And solvation is killing the tertiary. So this is like one of the paradoxes in acidity and basicity. We can add other groups to the nitrogen, and we won't have to worry too much about solubility. But the general rule for amines is, the more you push electron density into the nitrogen, the more basic the nitrogen will become. But this is the anomaly because solvation comes into play. Does that kind of make sense? I mean, it's a clumsy argument. Yes, no, we just tune out. What about rings? What happens when I attach my nitrogen to a benzene ring? What's its pKb? 9.4. Wow. Now, does that make sense? It may make sense from the solubility standpoint, because water, I mean, this stuff isn't going to be very water soluble, because it's got a big fat benzene ring on it. But there's something else going on here. And you might be tempted to go, oh, but wait, that nitrogen positive charge, won't that kind of like be distributed into the ring and the ring will stabilize it? Actually, it's just the opposite. The ring is going to pull the positive charge towards it. But it's not even that. It's at the beginning here. A benzene ring looks like this. All sp2 hybridized carbons in that conjugated system. What's nitrogen going to do? Nitrogen is going to orient its lone pairs so it's parallel to all those other p orbitals. And so it's going to like partially participate in that conjugated system. And what's that going to do? It's going to actually remove electron density from the nitrogen. And by tying up this lone pair partially in that conjugated system, that nitrogen, that's going to be less available to bond in H+, because it's part of the pi system a little bit. It's not completely, but it's partially part of the pi system. If it's partially part of the pi system, it's not available to take on an H+. And so that's why the pKb number went way up to 9, is because that pair of electrons is less likely to take on an H+ because it's part of the pi system. And so being part of the pi system means that the nitrogen is actually losing electrons. Does that make sense? All right, last ones then. Who's the stronger base? The one with the nitro group or the one with the methoxy group? Who's stronger base, A or B? Take a guess. How many people agree with A? Okay. B? What's the rule here? What's going to make this nitrogen a stronger base? I haven't answered yet. What's the rule? The nitrogen will become more basic if you push electron density into it. Okay, how are you going to push electron density into the nitrogen? You're going to have to push electron density of the nitrogen through the ring. Who's pushing electron density into the ring? B. B's pushing electron density into the ring. Because nitro's doing what? Withdrawing it. How do we know that? Yeah. The methoxy group is activating because it's pushing electron density into the ring. Nitro group is withdrawing electron density. So B would be a stronger base. And if we had their pKb values, we would say that nitro is 13 and the methoxy group is 8 points. So pretty significant difference. So can you forget about the chart? Well, no, you can't forget about it because the final's coming. But also you can't forget about it because there are times when we're going to use that chart to tell whether we're pushing electron density into the ring or out of the ring. So, I stress fundamental rules because we use them. So the fundamental rule here is going to be anything that pushes electron density to the nitrogen is going to make it a stronger base. Honestly, this approach is how I learned math in high school. My math teacher was like big on repeating back stuff to him. And so that's all he would do is just start the phrase and then point at somebody and say, finish it. It's not working here very well. Unless you're saying it in your head, which would be okay, but if it made it from here to here, that would be really good too. So that's why I'm stressing these fundamental things, because they explain a lot. And if you got them for good. Okay, so that's the basicity of amines. Of the NH2, yeah. Well, it's the pKb of the NH2 to form the NH3+. So if I gave you the NH3+, we'd actually have to go back and, as the book does, the book will give you NH3+, and it'll give you the pKa of the acid, of that as an acid. That's too many inverse relationships for me. That's why I'm giving you pKb and saying the pKb of the amine, because that's what we're measuring, is the ability of that nitrogen to pick up a proton. from the solvent. So 13, weak, 8.7, stronger. But there's still, you put a benzene ring on the NH2, what happens? The pKb goes up, which means it becomes much weaker. So in terms of the sequence here, it goes core, just generalities. Alkyl benzenes, stronger bases than ammonia, stronger than aryl benzenes, and each one of those has its subdivisions within it. But put a benzene ring on an NH2, becomes much weaker. Put an alkyl group on the benzene or on the nitrogen, it'll become stronger. Now, there's, divisions within that. Okay? So, that's the basicity of amines. So it's not completely simple here, because we've got a solubility issue, and we also then have attaching a benzene ring creates a weaker base. Okay. So those are the important physical properties of amines. You can go through and read some of the other ones. They talk about like some of the common amines that you have. Amines basically have an ammonia and or a fishy type smell. If you go to buy fish and it smells fishy or rotten, that's because of the amines that are in there. Some of which have very colorful names like putrescine, cadaverine. These are all amines that you find in dead fish. Cadaverine probably find in dead bodies too. So these amines have putrid smells. So that's the issue with them in terms of their physical properties. But basicity is the big one. All right, how do we make amines? Well, a couple of easy ways to make amines. I take a primary amine and I add NH3 to it. What's going to happen? Amine, ammonia, decent base, also decent. There's another phrase I've said over and over again. Strong base, strong nucleophile. So ammonia, strong base, but also a good nucleophile. Is it better than oxygen? See, that's what we do. We look at the periodic table and I say that. Is nitrogen better than oxygen? We look at the periodic table and we say, yes. Is it better than carbon? No. So ammonia or any amine can be used as a nucleophile. So that means if I react it with a primary halide, this reaction is going to be SN2. So the amine's going to come in, attack the carbon, kick off the chlorine, and I'm going to add my NH3 to it with the plus charge and then the Cl minus. This is a problem with amines. When we react them in SN2 reactions, we can't get rid of the H plus, and all of a sudden the Cl minus hangs around as a counterion. So whenever we're doing reactions of amines, they tend to protonate. But we know that because if they're in water, ammonia protonates anyway. So this can be a real problem in organic synthesis. If I want to make an amine, it's going to protonate, it's going to become ionic, and it's going to be dissolved in water. And so when I do my extraction, what's going to happen? Well, it isn't going anywhere because it's ionic and it's going to stay in the water layer. So if I did this reaction, I tried to get this product out by like extracting it with ether, I'm going to get nothing. Because this is ionic, it's going to be soluble in the water layer. So how should I make this kind of a neutral molecule? We make this a neutral molecule by adding hydroxide to it. And what does the hydroxide do? It basically deprotonates HCl, so that we end up with then an NH2 plus water plus then our Cl minus. So if you want to get the amine out of the water, you've got to make the solution strongly basic. Strongly basic. You might say, but that NH2 minus is going to react with water, bless you, and make an ammonium salt. True. So then we invoke the base plus water is in equilibrium with the BH plus hydroxide equilibrium, and we say, how do I push the BH plus back to being a neutral B? Now we can use Le Chatelier. So now I can say, okay, let's add the OH minus, and that's going to push the equilibrium towards B. If I add hydroxide, it's going to push this equilibrium back towards forming the NH2. But it is tough to get amines out of water. And so that's an issue you have to overcome. So there's going to be times when we do this reaction, we alkylate the nitrogen by adding an alkyl halide. That's always going to have to be followed by the addition of base, because otherwise I'm going to end up with my N plus species. So I always have to use base in order to make the neutral amine. Because this neutral amine can be a nucleophile, but not if it's a plus charge. If it's a plus charge, it's not a nucleophile anymore. So we have to do these reactions under basic conditions. So you can alkylate an amine all you want. I could take this NH2 minus and I could say, you know what, how about I add a methyl chloride to it? If I add a methyl chloride to it, the nitrogen will come down, react with the methyl chloride, and now I will end up with a nitrogen with one H on it, a methyl group. It'll still be protonated, so it'll still be the ammonium. There'll still be a chloride. Then what do I need to do? Add hydroxide, and that will then let me make my neutral amine. Can I do this again? Yes. Can I do it again after that? Yes. At some point I'm going to end up with an N with 4 alkyl groups attached to it, and then I'm done. So if you end up with a nitrogen with 4 alkyl groups attached, that's as far as you can go. And can I make one of those alkyl groups disappear? Alkyl groups are terrible leaving groups. So once I make my tetraalkyl ammonium salt, I'm done. Are they useful? Very. Trialkyl ammonium salts. You probably, if you do your laundry, you're going to be using a trialkyl ammonium salt. So they are used. And little side trip here. We talked about taking a triglyceride and hydrolyzing it to make soap in a saponification reaction. No, we haven't talked about that yet. So we will. This is a long-chain deprotonated fatty acid. Fat acid. Hydrophobic, hydrophilic. What happens to these things when you put them in water? They kind of do this. all the nonpolar tails get together, and all of the polar groups, which I've indicated as circles here, are water soluble, and so they form those. Anybody know what those are called? If they're arranged like this, if they're arranged like that, that is the perfect way to make a cell membrane. What do you say? When they're circular, they're called micelles. So using these hydrophilic, hydrophobic molecules can be done to make a membrane, or it can be done to make a micelle. The micelle part is actually useful in the laundry detergents, because if you have grease and nonpolar stuff on your clothes, what's going to happen? These hydrophobic tails are going to be attracted to that, and then the grease gets dissolved into the water because the grease is sitting inside of that cavity. And so the hydrophilic parts dissolve it. So this would be an example of a soap, a naturally occurring soap. We can make soaps this way, but most likely what we do is we make detergents. And so a detergent has a long chain, and what does it have on the other side? It's got a tetraalkyl ammonium. Same function. Only this is more of what you would find in a detergent. And those are synthetic, and we can make those all day long. You want to make a naturally occurring soap, we'll talk about that. You need fat or oils. So if you want to make soap, you can go to the grocery store and get a tub of lard. They probably still have. When I lived in Athens, the grocery store across the street had a lard section at the end of one of the aisles. Lard in all quantities. So it was easy to do that if you want to make soaps. But you can use coconut oil, you can use vegetable oil, you can use either an oil or a fat. And the difference between an oil and a fat is fat's solid, oil's liquid. Fats that are solid tend to have no double bonds in the chain, and oils tend to have double bonds in the chain. That's the difference between saturated and unsaturated. I have a feeling of deja vu that I've kind of gone off on that tangent sometime this summer. Right, and whether it's a solid or a liquid. So what happens with the double bond is it kinks the chain so that they can't pack on top of each other really well. So the more you could pack the straight chains on top of each other, the cumulative intermolecular forces, the London dispersion forces, are going to cause those chains to pack well, and you're going to end up with a solid. On the other hand, if they're kind of kinked, you can't pack them together, so they're a liquid. They don't pack well. Coconut oil is, I'm not sure what the double bond content is of coconut oil. It's a relatively low melting oil, though. So I don't know where it fits in the saturated, unsaturated, because there's always a controversy on whether it'll kill you or whether it's perfectly fine. Yeah. It really depends on where you go on the internet. In the biochemistry, if you have that double bond can react. I have no idea. Nutrition is not necessarily on my top 10 to-do lists. But that's what we have Mr. Internet for. But it's all about the double, it's saturated and unsaturated. Oh, I know where we talk about this. What happens when you hydrogenate a double bond? If you have a double bond in the chain and you hydrogenate it, what happens? You turn the unsaturated fat into the saturated fat, and if you don't quite get all the double bonds, you form a partially hydrogenated fat, which I guess those are the most evil things. Those are the most evil fats, are the partially hydrogenated things. I remember talking about that within the last 8 months. The spring and the summer are kind of merging together at this point. It's been a long summer. But it's not over yet, remember that. So, the idea is if you want to make something that will form micelles or even membranes, you need a hydrophilic and a hydrophobic group. If we're talking consumer products, if you look at your laundry detergent, you'll see either what's called an anionic surfactant or a cationic surfactant. Anionic surfactants would be something like this, although not quite, and a cationic surfactant would look like that. They're synthetic because we don't have enough lard to make soap for everybody in the world, or coconut oil, or whatever. But honestly, if you want to buy a foo-foo, bar of soap that's been handmade, you basically can just get, and we'll talk about this, you just basically get an oil, treat it with hydroxide, and you make the soap. So it's not that hard. You got to wash all of the hydroxide out of it so it doesn't burn your skin. Because they have other stuff in them, they have marketing, they have capitalism in them. I don't know if they're as complicated as shampoos, but they're probably complicated. Because they have moisturizers in them, they have scents, they have all sorts of stuff. But if you want to make your own soap, you can do that. That's the basics. That's the organic chemistry basics. We'll come back. All right, where were we at? We were at alkylation of amines to add alkyl groups to nitrogen. So that's the simplest way. Take nitrogen, nucleophile, react with alkyl halide, make the ammonium salt, but then you've got to treat the ammonium salt with base to get it back to the neutral amine. You can do that as many times as you want, but every time you do it, you got to use hydroxide to basically get rid of the HCl. So that's the simplest method to make amines. We will use that. But then there are some other methods that we can use based on reactions that we hopefully know. Called reductive amination. Now, reductive amination sounds pretty complicated. It is not. It is 2 steps. First thing I want to do is I want to react a ketone or aldehyde with NH3. Then I want to react that compound that I get with something else to make a primary amine. So I can use this series of steps to make a primary amine. React ammonia with ketone or aldehyde. I forget, what do I make there? I make that. Which in this case, this would be an amine. Because I did use ammonia. So I make my amine and How do I convert my imine to my primary amine? What do I have to do? Oh, I forgot an important part. What's the first part in this reaction? It's called reductive amination. So we could consider this the amination part. I want to get rid of the CN double bond. What should I use? And the catalyst would either be palladium, platinum, or rainy nickel. I was a little surprised they didn't give a specific there, but if you're in doubt as to whether the CN double bond can be reduced as easily as a CC double bond, just overkill and use rainy nickel. So if I use ammonia with my aldehyde or my ketone, I can make any primary amine I want. But the key is I used ammonia and then I made the imine and reduced it. You might say, okay, I want to make a secondary amine. Well, then I react the primary amine with my aldehyde or ketone. What am I going to make there? Imine or the shift base. This is technically what we would call a shift base. And then what am I going to do with my shift base? React it with hydrogen and rainy nickel. And now what have I done? I've now made a secondary amine. And I'm choosing this group from the ketone or aldehyde, and I'm choosing this group from the amine, primary amine that I use. So we can make a primary amine, we can make a secondary amine by reductive amination. Now let's make a tertiary amine. What's a tertiary amine going to look like? Tertiary amine is going to be taking my ketone or aldehyde and reacting it now with a secondary amine. And what am I going to make there? What? Yeah, what kind of amine? It starts with E. An enamine. So I'm going to make my enamine. So we've got the double bond. It's not to the nitrogen, it's to the carbon. Does it matter? No, because what am I going to do with this? I'm still going to treat it with hydrogen and rainy nickel. And what am I going to form? Two of the R groups came from the amine that I used originally. The other R group came from the aldehyde or ketone. So reductive amination, what it lets me do is it lets me basically choose whether I want to make primary, secondary, tertiary, and I can choose the alkyl groups that I want by choosing the aldehyde or ketone appropriately, as well as choosing whether I use what the R group is on the primary amine versus what 2 R groups are on the secondary amine. So reductive amination is pretty useful if I want to make a very specific primary, secondary, or tertiary amine. I just have to pick and choose what I want. Is there anything new here? Nope. This, yeah, because I put an extra R group in here because really what I should have done is I should have said this. There should be an R with the CH2 because that's where this double bond's going to come from. Okay, so that's reductive amination. So alkylation, only new thing about alkylation is you need to use base to get back to neutral amine. Reductive amination, I'm taking 2 reactions I learned, put them together to make the amine I want. And there's 2 or 3 other ones here that we'll pick up after our break. And then there are some reactions of amines that turn out to be fairly important, and they might take a little bit of time. Okay, so we'll start back up again at like 10:33-ish. So which one? All I did was I just brought that R back. At this point it should be there should be the CH2 here with the R there. The way I've carried it through. Yeah. I just combined it together for an R. Okay. So far each method we use to make an amine kind of has a plus or a minus. It's easy to do these SN2 reactions with ammonia or with an amine to alkylate it. The problem is you got to get the product out of water and you have to convert the ammonium back to the amine. The reductive aminations give you a lot more control over what the R groups you're going to attach, but I guess the disadvantage there is you got to do two steps. So another method that's that's classically used to make primary amines, and it even has a name associated with it, is the Gabriel synthesis. So the Gabriel synthesis actually starts out with this amide. So it's got a nitrogen attached to 2 carbonyl groups, and this is called phthalimide. PHTHALAMIDE. It's called phthalimide. And because the nitrogen is between 2 carbonyls, the NH is actually kind of acidic. so that we could react this with something like hydroxide, and we could remove that nitrogen, the hydrogen from the nitrogen. So we can actually make an N- out of the phthalimide to make basically an amide. So this is a decent nucleophile. And so what we can do is we can react this with any kind of primary alkyl halide, and it'll just simply do an SN2 reaction. It'll come in, kick off the chlorine, and we'll end up alkylating our phthalimide and putting that R group on the nitrogen. And there's no issue here about a positive charge on the nitrogen because I used an N- to do this reaction. And this nitrogen, for a number of reasons, which I'll get into when we talk about amides, that nitrogen is actually not very basic in terms of wanting to pick up the proton, so I don't have the water solubility issue. So I put my alkyl group on there, and now what I have to do is now I have to take into account the fact that this amide is a carboxylic acid derivative. And as a carboxylic acid derivative, whenever you treat it with H+ and water, you end up cleaving the nitrogen carbonyl group bonds, and we end up forming carboxylic acids. So we end up with 2 carboxylic acids here, and so we end up with the C double bond OOH. And this is actually called phthalic acid. If in general chemistry, if you've ever done a titration and you needed to standardize your titration with KHP, KHP has one of these 2 carboxylic acids deprotonated, and so the K stands for the potassium, and then the H for the carbonyl, and then the P for the phthalic acid. And what I end up doing then is I end up liberating the nitrogen to form a primary amine. And so this only really works with primary alkyl halides. If it gets too sterically hindered, it becomes a bit of a mess. But this is what's called the Gabriel synthesis. And it's a very old school way of making primary amines. Yeah, the whole synthetic scheme is the Gabriel synthesis. So you basically take a phthalimide, you would take an N-, react it with a primary halide, and then you hydrolyze the ester to form to liberate the primary amine out. It has the issue of once I use H+ and water to do the hydrolysis, I still got to get that out of water. And it's a nightmare to try and do that. I know because at one point, a long time ago, we took this molecule that I had purchased that had all the nitrogen enriched to nitrogen 15 for NMR, and we used 1,2-dibromoethane because I wanted to put these 2 groups on either side of the ethane, and then I wanted to hydrolyze them to make a molecule called EDA, ethylene diamine. And I wanted to make it with 2 N15 nucleus on it for NMR. And so it took us forever to get that compound out of the water. And you literally had to fill either the beaker or the round bottom or whatever you were using with sodium hydroxide pellets until you had just a little teeny tiny layer on top. And then getting the pellets out of that was a nightmare, but getting these products out of water is tough. But we used the Gabriel Synthesis. It was fine. We ultimately got what we wanted. We did NMR on it. So Gabriel Synthesis is a much more traditional approach. But again, it has its pluses and minuses. So this is specifically for primary amines. And then our last method of making specifically a primary amine is to basically take an alkyl halide and react it with azide. So azide is N3-. We haven't seen azide since like the first day or two of class, because this is a compound that has 3 different resonance structures, and so it's a nice one to make the resonance structures and then do the hybrid of. So azide, again, one of your nitrogens is going to have a negative charge on it. It can come in, attack the carbon, kick off the chlorine, so that we can make we can add that azide to the alkyl group. And so again, I'm just going to have the plus charge here. There'll be a lone pair there. And then over here would be the nitrogen charge, so that I'm neutral in this molecule, so I'd have 2 lone pairs there. Now, the problem with azide is that I have now made a molecule with an embedded gas molecule in it, an embedded gas molecule of N2. In general, that's bad, because whenever you embed a gas molecule into a molecule, it has a tendency, if it does decompose, it'll form a gas and explode. So what we then do with the azide is we very carefully make it, and we just treat it with lithium aluminum hydride. And when we add the lithium aluminum hydride to it, what we end up doing is we end up losing the N2 molecule and converting the one nitrogen into a primary amine. So azides can be used to make primary amines as well. So azides, Gabriel Synthesis, ammonia, and doing reductive amination. So we can make all those molecules. So right now we're at synthesis of amines. So these are all the methods we can use. The last one. Start with an alkyl halide and add cyanide to it. Cyanide, C triple bond N. Cyanide comes in, reacts with the carbon, kicks off the chlorine. It's just another SN2 reaction, but now I have a C triple bond N. I would now like to convert this to a primary amine, so I'm going to add lithium aluminum hydride to that. As a foreshadowing of adding organometallic reagents to carboxylic acid derivatives, because we talked about the C triple bond yesterday. That can be hydrolyzed with H plus H2O to carboxylic acid. And so when we did that, we formed the alpha hydroxy carboxylic acid yesterday. That means C triple bond N is a carboxylic acid derivative. I can add organometallic reagents to to these carboxylic acid derivatives. The first one I'm going to add is H minus. So I could write the product here, and I could just say, oh, well, we're going to form a primary amine, because we're going to reduce the C triple bond N down to a C single bond and add nitrogens all the way around. But we know the mechanism of this. Sort of. Unless it has some magical step. So let's talk about the mechanism of that, since it's a review. So let me take my C triple bond N, and I forget, I really don't, but what's lithium aluminum hydride a source of? H minus. How many? Up to 4. So my H minus is going to attack something. What's it going to attack? Carbon or nitrogen? Then what happens? Pair of electrons goes to the nitrogen. I have an N minus. Oh, this has a magical step. It has one lone pair, it has 2 lone pairs, and that's what gives it the negative charge. So I'm showing the negative charge as the other lone pair. So, let's see, do I want to show the magical step at this point? I could. All right, so my AlH4 minus lost an H minus. So it becomes AlH4 neutral. AlH3 neutral, sorry. Okay, so it forms an AlH3 neutral. I'm going to write this in AlH2 because I'm going to do something with the other H. Now, aluminum is like boron. It's in the what is that one? It's in column 3 of the periodic table. So aluminum can actually take on an extra pair of electrons just like boron can. So what happens is that the nitrogen bonds to that aluminum. So now I've got an aluminum with an 8 with 3 H's on it. Okay. And if I did that, then the aluminum would, so it's just going to form that bond. So then what's going to happen? What's next going to happen is this. Another H minus is going to come attack that carbon, and the pair of electrons is going to go to the nitrogen. So now in this case, I've now added 2 hydrogens to my carbon. My nitrogen now has a negative charge. And that negative charge, the aluminum then picked up a positive charge because it just lost an H minus. So now I'm going to form a full-blown covalent bond there. Okay, so this nitrogen has basically a negative charge. So Well, actually, sorry, it doesn't. It gave its negative charge to form the aluminum bond. So now I have reduced the carbon down to a CH2, and then through a series of steps, which I'm not going to go through, we basically get rid of the aluminum so that we can now, the nitrogen will end up picking up 2 hydrogens. And so I will have reduced my carbon and my nitrogen down to a single bond. And so when you reduce with a lithium aluminum hydride a nitrile, you end up with a primary amine. And like many of these organometallic reagents, there is an issue of the aluminum actually being involved. So that's another way we can make it. We can make an amine. So lithium aluminum hydride reduction of C triple bond N is basically like adding H2s, 2 H2s. So that's how we make amines. Now we need to react them. And there's many different amine reactions we can do. Let's review. We can do electrophilic aromatic substitution when the nitrogen is outside the ring. And so if I do that reaction, where does the E plus end up? It's going to end up orthopara because NH2 is what kind of group? As a matter of fact, it is the most activating group. When did we at last have to do this? Yesterday. All right. So what can we do with that? We can do electrophilic aromatic substitutions on what are called anilines when you have a nitrogen attached to a benzene ring. What else can we do with amines? Well, we can turn amines into amides. So if we react an acid chloride with a nitrogen, with an amine, we will make an amide. Where did we see a similar reaction? If you take an alcohol and react it with a carboxylic acid chloride, what do you make? An ester. So if you can react an acid chloride with an OH group and make an ester. You can react it with an NH2 group or even an NH, I suppose, and make an amide. So you can make the amide, or you can make same reaction we use for an ester. All right, great. So we can do that. Let's expand this a little bit, and we can take a little diversion here for a couple things. We can react the amine. We could react an amine with a sulfonyl chloride. And if we did that, what would we make? The nitrogen equivalent of a starts with T of a tosylate ester. So we can make the nitrogen equivalent of a tosylate ester here. Which might be something useful to make. Now there is an entire synthesis of nitrogen compounds that I'll show you. And it actually involves something similar to this with the sulfonyl chloride groups, but it is useful in terms of making a class of drugs that has basically some historical significance. So the molecules that we can make are what are called sulfa drugs. And so the generic structure of a sulfa drug looks like this. And this is in today's folder. But I just want to show you this. This is the overall classification here of a sulfa drug. Let me go into slideshow mode. So, in a sulfamide drug, what you end up doing is you end up adding you have a nitrogen group attached to the ring. You have an SO double bond 2 group, and then you have a nitrogen group on the other side of that sulfur. And so we'll go through here quick because actually we know the reactions that we can use to make this molecule. So we can make our sulfamide, we can make these sulfa drugs. Now why are sulfa drugs important? Because basically in World War II, sulfa drugs were used, they were developed to help stop infection. And so, as this book says, they were the first miracle drugs. This was actually called chemotherapy at the time. It's not the chemotherapy that we think of now. but any kind of therapy to cure cancer with a chemical would be chemotherapy. We don't necessarily have to think about radiation or anything like that. So in World War II, what happened was that the soldiers were given sulfa drug in kind of like a gum wrapper or a small envelope in a metallic casing that they could have, and if they were to get injured, they could rub the sulfa drug on their wound, and that would help keep it from getting infected. Probably would have been nice to have this in World War I, because it wasn't so much injuries as it was the infections that caused, people to lose limbs, because your leg would get infected and they'd have to cut it off. Civil War even worse than that. So people were given this drug, and during this time, these were so important that Walt Disney made this war cartoon for sulfa drugs, and their animators had a fantastic time making this. I don't even know if am I allowed to zoom in on this? Stop. How come it zooms in on everything except what I want it to zoom in on? Anyway, this is a real life cartoon. And then you have, at some point in the second to last cartoon slide, it says chemotherapy. So this is where that term started to be used, the idea of using chemicals to treat disease. At this point, it wasn't cancer, it was disease. And so they were doing this is, your typical war propaganda, to sort of show people that these drugs were as important as, they say, as important as bullets, in terms of winning a war, because if you had a wound, these kept them from getting infected. And so the idea that you could develop these drugs to treat these different diseases, and there's more than just that disease on there, then what happens is that they started to think about developing more and different kinds of drugs to treat those. Cameron, what were you going to ask? What were you going to ask? They said the animators had fun with this. There's all sorts of things. There are some different diseases on here that are listed, so that these sulfa drugs would treat. But then you have to talk to the Dr. Dog down here at the bottom, because these are very potent drugs. You just shouldn't take those, or you end up like Mickey two things later with a headache and a rough tummy. So they were very potent drugs, but this is, if you Google search like Walt Disney sulfa drug cartoon, this is one of those things that they're like, nobody can believe that Walt Disney animators did this, but they did. I have an original copy down in my office, my other office, that I got. It's like 1940 something. So sulfa drugs, then, how do we make them? How can we make the sulfa drug? So how can we make the sulfa drug? Let's see. Do I have anything not written on? No. Which means I need to get out of this one and go back to my other one. So how can we make those kinds of molecules? You tell me. I have a benzene. I want to put an NH2 group on the ring. How should I do that? Fe or 10. So put a nitro group on the ring, reduce it down to NH2. And we can put the NH2 group on the ring. All right, I want to put the In the sulfa drug, we have an NH2 we can start with, and then down here we need to put on an S double bond O OH group. I need to put on an SO3H group onto that ring. How should I do that? Want to make a sulfonic acid. SO3 and H2SO4. So that'll put the sulfonic acid group on the ring. Nitrogen being an ortho-para director, the sulfonate's going to go on ortho or para. This is one of the places where I make my argument for sterics, and I say there is no way this big group is going to fit ortho. There's no way that large group is going to fit ortho, so I'm going to get nearly 100% of just para, which is what I wanted. Okay, so now what I'd like to do is I'd like to add a nitrogen group to the sulfur. So we already know how to do that, right? I just need to take my molecule and I need to convert that to a Cl, and then I can add a nitrogen group and put the nitrogen onto the sulfur. So how do I convert the sulfonic acid to the sulfonyl chloride? What do I need? I need a reagent whose only purpose is to convert OHs to Cls. SOCl2 or PCl3, PCl5. That converts the sulfonic acid to a sulfonyl chloride. And then when I add the nitrogen to the sulfonyl chloride, I would add the nitrogen to the sulfur ring, or the sulfur part of the ring. Because remember, when I react SO3H and H2SO4, the electrophile that I'm adding is SO3H plus. And so SO3H plus looks like this. With the plus. So SO3H plus looks like that. So the OH is part of the SO3H plus. And so that's how I can make, depending on what amine I want to use with my sulfonyl chloride, I can put any amine group on there. I could take this NH2 minus at the end of this, and I could say, oh, I want different alkyl groups on there. And so now what I could do is I could just simply alkylate that nitrogen. Or I might want to even turn it into an amide. So the whole class of sulfa drugs had different nitrogens attached to sulfur and different nitrogen groups attached to the ring, but this is how I could construct them. And this is how people made the different classes of the sulfa drugs to treat whatever disease they wanted to try and treat. And so originally they just started out to be basically an infection prevention drug. But then later on they were used, and probably still are to some extent, used to treat all sorts of different diseases. So this is not drug development by any stretch as how it looks today. This is a little more sophisticated than taking birch tree bark and the salicylic acid and adding an acetyl group on it so it doesn't rip your stomach apart to make aspirin. A little more sophisticated than that, but this is where our drug development has come from through the years. And so this chemotherapy idea existed long before we're talking about chemotherapy for cancer, for cancer treatment nowadays. But it's still the basic same principle. You're using a chemical to treat a disease or to kill something, which is what the cartoons were showing. Things killing other things. So that classification of sulfa drugs is an illustration of electrophilic aromatic substitution, the sulfonyl chlorides, and then alkylating the amines if necessary. Okay, so that's another series of drugs, or a series of reactions we can do with amines. Now I want to go back to electrophilic aromatic substitution. We're going to have to do Cope and Hoffman elimination. Hoffman elimination should ring a bell because there's the Zaitsev product and there is the Hoffman product. And where did the Hoffman product come from? Back in the Organic 1 class. It will come up tomorrow, which is why I sometimes don't even use the Hoffman term, because I'm like, you're going to have to wait until next semester to learn it. Tomorrow is next semester. So we'll talk about Hoffman elimination, which we automatically will know will give us the double bond that is least substituted. But Hoffman and Cope have some other issues. Now, the last thing I want to talk about is this. Maybe I should turn this into a take-home quiz. So, and sadly I did skip the aromatic, how something is aromatic or not aromatic. I may come back to that by the end of next week. So, here are two what are called hetero cycles. They have the nitrogen, oxygen, sulfur. Those are hetero atoms inside of a ring. So these are called hetero cycles. And there's a lot of chemistry that goes on to hetero cycles because, well, I don't know. If you think about hetero cycles, for those of you that are biology majors, if I was to sort of show you a molecule that kind of looks like that with a nitrogen in sort of a fused membered ring, what is this reminiscent of from biology? That's the best I can do. What holds DNA together? No, proteins are amino acids. Hydrogen bonding of what? I think that might be... Isn't it like the ATCG? Which are also sometimes called... They're also sometimes called like the base pairs. So, when you start putting nitrogen into aromatic rings, you start making the basics of DNA so that you can hydrogen bond those together to hold the double helix together. Now, why, if I'm going to sit down and design DNA, you know, hydrogen bonding is strong, but yet it can be broken. And I think you take DNA and you kind of break it apart right, and then it does something, and then it comes back together again. I have 1 semester of biology under my belt. 2nd semester senior year. Sadly, the freshmen that were in that class did not benefit from a curve. It's easy to break the curve when you're a second semester senior taking biochemistry and general biology at the same time. They didn't like me, but I didn't care. So, don't have that much biology background, but if I was to sit down and design it, I'd say, well, okay, they got to come apart, so maybe hydrogen bonding. Lots of hydrogen bonding is going to hold them together tight, but they still can come apart. And I'd say, well, that inner core, I don't really want it reacting because it's DNA, and if I'm going to use DNA for replication and other things, I don't really want to mess with it because then it's going to mutate, and, you know, if my DNA mutates, if it can give me superpowers like being able to do dishes and laundry faster or just wave my hand, that's done, I'll take that superpower, but chances are my mutation is going to kill me. So we don't want things to mutate. So what am I going to put on the inside? Aromatic compounds, because they're super stable. And they're flat, so I can form my hydrogen bonds really nicely, right? So if I'm the ultimate designer of DNA, I might think about that. Or this just might randomly happen over the course of 6 billion years. Okay. That question is for another class, somewhere else, right? But if I do electrophilic aromatic substitution on these molecules, where is the E plus going to go? Is it going to go to position A, B, or C? Or is it going to go to position A or B? And here's what I would like you to do for tomorrow. I would like you to add the E plus to carbon A and write all the possible resonance structures. And then I would like you to add E plus to B and write all the possible resonance structures. And then I would like you to add E plus to carbon C and write all the possible resonance structures. Where is E plus going to add? The one with the most resonance structures or the combination of the resonance structures that are most stable. So you might get a resonance structure in here. It's not going to be very stable. But I'll let you write them out and then we'll decide tomorrow whether they're stable or not. And then I want you to do the same thing for this 5-membered ring. Write the different resonance structures. So where's the E plus going to go? That's how we have to determine it. We didn't do this with the electron donating and withdrawing groups. We did this really quickly. But this is what I would like you to do, to write all those different resonance structures. And then tomorrow what we'll do is I can randomly ask people to give me their resonance structures. And then we will interrogate them to determine whether they are correct and whether or not we'll interrogate them in a friendly, positive way. And then we'll figure out, okay, where should the E plus go? Okay, and then we'll talk about Cope and Hoffman, and then we'll talk about carboxylic acids tomorrow. Consider doing this a take-home quiz. Getting it exactly right, I won't necessarily grade it on super correctness, but I will grade it on whether you did it or not. And I'll have your exams tomorrow.